Imagine for a second making like one single typo at your job.
Oh, no.
Right. Just
Yeah.
one typo. And it instantly costs your company $50 million.
Yeah, that's a bad day at the office.
No second chances, no undo button, nothing. And that is actually the daily reality in the high-stakes world of advanced microchips.
It really is.
But what is truly fascinating about this entire industry isn't, the billion-dollar machines actually printing the chips.
Right.
It is this completely invisible software gatekeeper that quietly decides if those chips are even allowed to exist in the first place.
Yeah, and that gatekeeper operates in this sector that honestly, most people outside the industry have never even heard of.
Right, totally invisible to the public.
Exactly. Because whenever we discuss, the absolute limits of human engineering, our minds naturally gravitate toward the physical bottlenecks.
We obsess over the hardware.
We do. We picture those massive, like truck-sized EUV lithography machines.
Oh, the ASML ones.
Yeah, manufactured by ASML.
Which are just the absolute apex of modern manufacturing. I mean, I was looking at the sources, and these machines cost anywhere between 180 million and nearly 380 million euros a piece.
Staggering.
And ASML is projecting over 4 billion euros just in research and development spend for 2025 alone.
Just for R&D, yeah.
So without them, the physical production of cutting-edge computing hardware simply stops cold.
It does, but, long before a chip design ever reaches those heavily guarded foundries, it has to pass through an entirely different filter.
Okay, let's unpack this, because the mission for today's deep dive is to figure out how this relatively obscure software layer is secretly dictating the future of global tech, AI development, and really what kind of hardware innovation is actually possible. So to start, we need to understand what this software, which is called EDA, actually does.
Electronic design automation.
Because if I'm picturing an engineer designing a chip, I'm just picturing a highly complex digital drawing board, like a really intense version of Photoshop or AutoCAD.
And that is the common misconception we have to break right away.
Okay.
EDA is not a digital canvas.
Huh.
A modern advanced chip contains literally billions of tiny transistors.
Billions.
Billions. So an engineer is not simply, dragging and dropping components or drawing lines to connect them. The sheer mathematical volume of layout options and routing combinations for those microscopic wires is entirely beyond human comprehension.
Because you aren't just connecting point A to point B.
No, not at all.
You're dealing with the actual physics of electrons moving at scale. You have to balance timing, heat dissipation, and power distribution across a piece of silicon the size of your fingernail.
Exactly. So EDA tools utilize highly complex optimization algorithms and increasingly machine learning to radically restrict the search space for the engineer.
Restrict the search space?
Yeah. The software evaluates the physics and constrains the possibilities. So it tells the engineering team, explore these 10 viable design pathways instead of a billion theoretical ones.
Wow.
It serves as this active, invisible filter.
So it acts more like a highly opinionated spell check for physics.
That's a great way to put it.
But if the software only recognizes established patterns, what happens when an engineer introduces a fundamentally new architectural innovation? Like if the software doesn't know how to spell this new idea, does the innovation just die in the simulation?
Well, what's fascinating here is that it faces immense structural friction, which creates what industry insiders actually call the EDA tax.
The EBA tax.
Right. So let's say a company is choosing between two competing chip designs. Design A represents a standard incremental improvement. It perfectly matches the established EDA workflows and the existing intellectual property blocks.
It's a safe bet.
Exactly. But Design B is a massive architectural breakthrough, but it requires custom routing and just doesn't fit neatly into the current software ecosystem.
So physically, Design B might be the vastly superior chip. It could process more data, run faster, generate less heat.
Yes. Economically, however, Design B is hit with that massive invisible tax.
What?
Because the software doesn't natively support this new architecture, the engineering team has to manually force the design to work within the tool's parameters.
Oh, that sounds like a nightmare.
It is. They take on significantly more risk of failure, and they lose precious time to market. So EDA inadvertently acts as this gravitational pull, dragging the entire industry towards safe, established paths.
So it's quietly dictating which innovations are actually economically viable.
Precisely.
Anyone listening who has ever tried to introduce a new software tool at a corporate job, knows this exact pain.
Oh, absolutely.
Like, the legacy system might be completely clunky, but it is trusted. So the new, better idea gets taxed to death in meetings, endless workarounds and approvals until people just give up pitching it.
It is the exact same dynamic, just scaled up to a level where it dictates the global pace of computing power.
And the financial penalty for getting it wrong is just staggering.
Yeah,
Like we mentioned earlier, the sources note that for a cutting-edge 3-nanometer chip, a single failed manufacturing run can cost over $50 million.
it's wild.
And that is just the hard cost of the silicon on the foundry time. It doesn't even factor in the devastating opportunity cost of missing a product launch window in a hyper-competitive market.
Right, which could be billions in lost revenue.
Yeah.
And that extreme financial risk completely reshapes how companies compete.
How so?
Well, the natural assumption is that the company with the smartest architecture wins the market. But the reality is that the ultimate competitive advantage is having the lowest cost of failure.
Ah.
The industry refers to this concept as experimentation speed.
Experimentation speed. Basically how fast you can afford to fail.
Exactly. Chip design is a highly iterative process. An engineer designs a block, runs a simulation, hits a timing error, and has to start over.
So if company X can run that learning loop 1,000 times in a month, and company Y can only run it 50 times.
Company X will inevitably end up with the better chip. They can simply afford to explore more options and refine their design further.
But how are they running thousands of loops without spending $50 million every time they test something? Like, the sources highlight the massive growth of hardware emulation, but how exactly does a company pretend to build a chip before physically building it?
So they utilize specialized supercomputers designed specifically for emulation.
Okay.
And there is a difference between software simulation and physical hardware emulation.
What's the difference?
Software simulation runs on standard servers and mathematically models the chip, which is incredibly slow for large designs. Emulation, on the other hand, uses thousands of programmable logic chips, known as FPGAs, to physically mimic the exact logic gates and wiring of the unbuilt chip.
Wait, so they are literally wiring up a massive temporary physical brain just to see if their theoretical brain works?
Yes, the emulator behaves electrically, just like the final product will, only running at a slower speed.
That's incredible.
It is. And this sector is booming, seeing roughly 40% year-over-year growth.
Wow.
The top 10 clients in the industry now rely on both software simulation and physical emulation hardware simultaneously.
Because they are absolutely terrified of that $50 million typo.
Exactly. Which brings us to the final hurdle in this entire workflow, which is the concept of sign-off.
Sign off.
Yeah. Sign-off is where EDA truly proves its worth as a trust machine.
Okay.
When an engineering team hits the sign-off button, the EDA software generates mountains of physical verification reports, power analysis, and timing proofs.
So it's building a case.
Yes. It manufactures the confidence required for a company's executive board to officially sign off on that $50 million manufacturing gamble.
So if the underlying value of the software is all in the trust, what happens if I start a company tomorrow with a genuinely faster, better algorithm for chip layout?
Good luck.
Can I break into this market and disrupt it?
You would face an incredibly tight oligopoly. Between 70 to 80% of global EDA revenue is locked up by essentially 2 global leaders and 1 major European vendor.
Synopsys, Cadence, and Siemens EDA.
Exactly. A startup cannot simply dethrone them with better code, because no chip company on Earth wants to be your guinea pig.
Because if my new, unproven software guarantees a design is flawless and it fails at the foundry, the chip company eats the $50 million loss, not me.
Bingo. Startups in this space usually spend years performing secondary, non-critical analysis.
Just to prove themselves.
Yeah. It takes a decade of a tool simply existing alongside the established giants before any major player will trust it with that final critical sign-off step.
That's a huge moat.
The competitive moat isn't just the technology, it is the accumulated trust of not ruining a multi-million-dollar manufacturing run.
That is a massive barrier to entry, but the industry is being forced to adapt anyway because the physical constraints of these chips are changing how everything is built.
Right.
Here's where it gets really interesting. If making a single chip is a $50 million gamble, and we literally cannot squeeze transistors any closer together without them melting, the industry has to find a way to cheat physics.
And they are.
They can't build bigger, so they are building modular. They are pivoting to what are called chiplets.
Right. instead of carving one massive, incredibly complex circuit on a single piece of silicon.
Which is prone to manufacturing defects.
Exactly. You carve out several smaller, specialized chips. These are the chiplets. You then package them closely together on a single base.
But slicing a complex problem into smaller pieces doesn't actually eliminate the complexity, it just relocates it.
Precisely. It moves the problem from inside the chip to the microscopic spaces between the chips.
Oh boy.
And this introduces a completely new set of physical nightmares.
Like what?
Well, how do you dissipate the heat when multiple high-powered chiplets are sandwiched together? How do you distribute power evenly across the gaps? And critically, how do you manage memory consistency?
Right, because if one chiplet updates a piece of data, every other chiplet needs to know about that update instantly. Otherwise, the calculations fall out of sync and the whole system crashes.
Exactly. The industry relies on protocols like CXL or Compute Express Link to manage this coordination.
Okay, CXL.
CXL acts as a high-speed translator, ensuring the CPU and the memory of all these distinct chiplets are perfectly synchronized, sharing the same mapped memory space without creating bottlenecks.
And coordinating that protocol requires incredibly sophisticated EDA tools.
Extremely sophisticated.
And to physically connect these chiplets, you need standard highways for the data to travel on.
Right.
The sources mention UCIe, which is a standard physical interconnect backed by over 120 companies. But the most fascinating shift here is the move toward optical interconnects.
Oh, this is wild.
They are looking at replacing electrical copper wires with light.
Yeah. When you push massive amounts of data through tiny copper wires at high speeds, you generate immense heat and electrical drag.
It just melts.
Right. So to bypass that physical limitation, the industry is integrating microscopic lasers directly into the silicon.
Lasers in the silicon.
Yes. They pulse data as light across tiny fiber bridges between the chiplets.
I mean, it solves the heat and speed problem, but now the EDA software has to suddenly understand optics and photonics, not just basic electronics.
It is a massive leap in simulation requirements. The software has to model the physical behavior of light interacting with silicon alongside the traditional electrical pathways.
That is just, it's mind-blowing. And all of this compound complexity explains why the AI-assisted EDA market is projected to completely skyrocket.
Absolutely.
We are looking at a jump from $4.2 billion in 2026 to nearly $15.9 billion by 2032. That is a 24% annual growth rate.
It's massive.
But how is AI actually functioning here? Is it just drawing the lines faster?
AI is certainly used to automate the repetitive drawing of routing wires, but the far more profound application is utilizing AI as corporate memory.
Corporate memory. Wait, if an engineer's knowledge is largely undocumented intuition just living in a senior employee's head,
Sure.
how does an AI system actually ingest it? It cannot read minds.
No, it cannot read minds, but it can read decades of unstructured error logs, revision histories, and bug reports.
Oh, wow.
Consider a 20-year veteran engineer. They know that a specific circuit arrangement will inevitably cause a hyper-specific timing bug because they saw it happen 10 years ago.
Right.
But when that engineer retires, that institutional intuition usually vanishes.
And the next generation of junior engineers has to hit that exact same wall and make the same multi-million-dollar mistakes to relearn the lesson.
Exactly. So EDA companies are solving this by building AI systems that ingest a company's entire historical log of failed simulations and successful workarounds.
Okay.
The AI acts as an immortal senior engineer looking over your shoulder.
That is so cool.
Right. If a junior engineer starts routing a design toward a known historical pitfall, the AI flags it immediately based on patterns from a decade ago.
So the software evolves from being a static tool into an artificial colleague?
Yes. And EDA companies are heavily leaning into this shift. They're transitioning to a three-tier pricing model where they actually charge for these AI agents as virtual engineers, right alongside standard software licenses and compute usage.
But there is a huge structural hurdle here, which the sources refer to as the data paradox.
Ah, yes.
AI models require mountains of data to learn those intricate patterns, but a chip company's design data is their absolute most guarded crown jewel.
Without a doubt.
In fact, 60% of EDA workflows still run on local, on-premise servers because these companies flat out refuse to trust the cloud with their intellectual property.
And you can't blame them. The EDA company that wins the AI race will not necessarily be the one with the best baseline algorithms. It will be the one that figures out how to train sophisticated models without breaking customer trust or commingling highly classified IP.
It is like a global banking network trying to build a universal world-class fraud detection algorithm, But none of the local branches are actually allowed to share their customer transaction histories with the central office.
This is an excellent comparison.
It seems impossible.
Well, the industry is actively exploring techniques like federated learning to bypass this.
What's
In federated learning, the AI model travels to the local on-premise servers, learns from the protected data on-site, and only sends the updated mathematical learnings back to the main system.
So the data stays put.
Exactly. The actual chip designs never leave the building. But maintaining that delicate balance of security and machine learning is incredibly difficult.
Let's zoom out a bit and look at how this software layer is shifting power dynamics across the entire tech landscape.
Okay?
Take a scenario where Company A and Company B both use the exact same physical foundry, like TSMC, they both use the same memory components, and they both use the exact same EDA software to design their chips.
Right. Yeah.
If the tools in the factories are identical, where does the competitive advantage actually live?
Well, if we connect this to the bigger picture, the advantage has migrated up the value chain.
Okay.
It is no longer just about who can manufacture the best generic transistor.
Yeah.
The true advantage is in product definition and whole system integration.
What does that mean in practice?
It is about knowing exactly what the hardware needs to do in its final environment.
Which perfectly explains why companies that don't own a single chip factory,
Yeah.
companies like Google and Amazon, are completely dominating the custom AI chip space.
Yes. Because a traditional semiconductor company builds a generalized chip, hoping it performs reasonably well for everyone.
Right.
But Google and Amazon deeply understand their specific server farm workloads, their proprietary AI algorithms, and their exact cooling capabilities. They use EDA tools to design hyper-specialized chips that run circles around generalized hardware for their highly specific needs.
The real value is in knowing the exact question, not just owning the calculator.
Exactly. And this shift toward whole system design is changing the EDA companies themselves. One of the sources points out that a major EDA player spent around $35 billion in mid-2025 to acquire a mechanical and physics simulation company.
35 billion.
Yeah, because designing a chip is no longer solely an electrical engineering problem. It is a mechanical problem, a thermal physics problem, and a structural problem.
Because of the heat and the packaging.
Right. If your chip runs perfectly in a digital simulation but physically melts when you plug into a crowded server rack, the chip is useless. EDA software has to expand to simulate the entire physical reality of the device.
And we also cannot ignore the geopolitical reality of having so much structural power concentrated in this single software layer.
No, we can't.
The sources mention that in May 2025, the U.S. Commerce Department tightened EDA export controls to Chinese clients, though they rolled them back by early July amid broader trade negotiations.
Yeah, and regardless of way anyone stands on that, it clearly demonstrates that EDA is viewed as a primary geopolitical lever.
It's a strategic choke point.
It is. The leading local EDA firm in China, Wada Empyrean, generates about $160 million annually.
Okay.
That is a mere fraction of the billions generated by the established global giants.
So the analysis in the sources asks a really vital question here. What does true semiconductor independence actually look like for any nation? Is the goal to replace every single line of foreign software to achieve absolute parity?
Well, the immediate strategic goal isn't parity. It is the elimination of single points of failure.
Okay, that makes sense.
If your national tech sector relies on a workflow where one revoked foreign software license halts all domestic innovation, you are highly vulnerable. Building domestic capability,
Even if it's not the absolute best.
even if it is trailing edge rather than bleeding edge, it creates a necessary buffer.
And a significant amount of that resilience is being built through open source architectures like RISC-V.
Yes, RSCV is a huge part of this. It's an open source instruction set architecture, meaning companies and universities can design processors without paying hefty licensing fees to established corporate players.
Right.
Now, an open source RSCV toolchain is not going to beat the multi-billion-dollar proprietary EDA tools today.
But it democratizes the learning process. It allows universities and startups to actually design, test, and build chips without massive upfront capital.
Exactly. It builds the foundational talent pool.
Mm-hmm.
Because the global war for semiconductor dominance is ultimately a war for experienced talent.
Right. You need the brain.
You meet engineers who have developed the intuition to interpret a complex timing report or navigate a dense physical simulation. Universities using free open source toolchains are training that intuition right now.
Which prevents a catastrophic talent choke point a decade down the line.
Exactly. You're building the soil so the ecosystem can grow rather than just trying to buy the tallest tree.
I love that analogy. When you step back and look at it, the semiconductor industry isn't just a simple assembly line where you hand a blueprint to a factory.
Yeah.
You have the foundries making the physical silicon. You have PDKs,
Process design kits.
right, the process design kits, which are essentially the physical rule books provided by those foundries. You have the intellectual property blocks. And tying all of these discrete elements together is the EDA software.
None of those pieces function in isolation. They are completely interdependent.
So, what does this all mean for the listener? I mean, it seems like the ultimate competitive moat in technology isn't a single patent, it is not holding the rights to a specific algorithm. The real moat is an ecosystem's ability to learn quickly, to fail cheaply through experimentation speed, and to convert that hard-won experience into automated workflows faster than anyone else.
The speed of the learning loop is the true asset.
And I think this concept extends far beyond silicon circuits. The EDA tax we talked about, it's everywhere.
It really is. Every highly specialized, highly complex industry has its own invisible screening mechanism.
Yeah.
It might be an internal audit process that is notoriously difficult to navigate, or a resource allocation algorithm that heavily favors legacy projects over risky new ventures.
Or it might just be an unwritten cultural standard within a company about what a good idea actually looks like.
Exactly.
If an idea doesn't fit the existing workflow, it pays the tax. It takes longer, it faces far more scrutiny, and eventually people just stop pitching those kinds of ideas altogether.
Because it's too much friction.
Right. The physical cranes might be ready to build anything, but the digital zoning software says no.
So true. And I think the final takeaway here is to look at your own profession and your own company.
Yeah.
What is the invisible, boring-looking software or that tedious workflow process that is secretly acting as the ultimate gatekeeper? Because finding that is the key to understanding who really holds the power in your field.